Hey Calculus, we are going to solve some volume disk problems. So the first thing we have to do is sketch our graph. So for problem number 1, we are rotating the region under the line, x plus 1, which is right here, from 0 to 3, and we're rotating it about the x-axis. All right, so the first thing we want to do is we want to put in a rectangle. So remember, in volume, the rectangle is perpendicular to the axis of rotation. So if we're rotating it about the x, we need a perpendicular rectangle. So that would be a horizontal rectangle, which will look like this. So there's our rectangle. All right, so now to help us visualize what this disk is going to look like, let's reflect this line across the axis of rotation. So it's going to look like this. And your disk will come in just like this. All right, so that rectangle will give us a radius of y, because that is a vertical length, and the thickness of the disk right here, that is a horizontal length. That is our change in x, and that is our height. Okay, so let's set up our definite integral. We need the area of the base times the height. All right, and the shape of the base of a disk is a circle. And the formula for the area of a circle is pi r squared. And our height is the thickness of the disk. That is represented by dx right here. All right, now we can replace the radius with the y. So it's going to look like this. We're going to have pi y squared dx. And then finally, we can plug in what y is equal to. My y, I plug in right here, y is equal to x plus 1. So that goes right here. So there is my integrand. Pi x plus 1 squared dx. All right, now we can plug in our limits. Our limits are along the axis of rotation, so they're from left to right along the x-axis. They are from 0 to 3. So we put those in right here, 0 to 3. All right, and there is your definite integral, and that is your goal for every volume problem. Now, before we solve this using the fundamental theorem of calculus, I'm going to expand this squared, because if I multiply this out, I'll be able to use the power rule when I take the antiderivative instead of use substitution. So that's going to look like this. All right, I'm going to go from 0 to 3, and I'm just rewriting this. So pi comes along, and x plus 1 squared is the same as x plus 1 times x plus 1. Now, if I multiply that out, x plus 1 squared gives me x squared plus 2x plus 1, either using the FOIL method or the area boxes. Now I am ready for the fundamental theorem of calculus to solve this definite integral. The first step is to find the antiderivative g of x. So the pi comes along for the ride. This is 3 power rules. The antiderivative of x squared is x to the third over 3, and I'm going to write that as 1/3 x to the third. The antiderivative of 2x is 2x squared over 2. The 2's cancel, and I'm left with x squared. And finally, the antiderivative of 1 is x. And I use brackets to bring along my limits. So that is the first step of the fundamental theorem of calculus. Now the second step, I plug in the upper limit 3 into my antiderivative, and I plug in the lower limit 0 into the antiderivative, and I subtract. So when I plug in 3 into my antiderivative, I get 65 0.97. And when I plug 0 into my antiderivative, I get 0. So my volume is 65.97 units cubed. There you have it. Number 2, we are going to rotate the parabola 3x minus x squared, the portion of it that is in quadrant 1, and we're going to rotate that about the x-axis. So my region looks like this. I'm going to highlight it for you. Okay, so there's our region. Let's put in our rectangle. It has to be horizontal since we're rotating it about the x-axis, and then it helps to kind of reflect that curve across the x-axis, and then our disk is right here. So we have radius y, and we have a height, our thickness of our disk, dx. So our integral is from 0 to 3. Your limits are along the x-axis, so the farthest part of the region here is 0, and the farthest part of the region on the right is 3. And we need pi r squared, but our radius is the y, so pi y squared, and our height is dx. So that is area of the base times the height. Now we're going to plug in what y is equal to. So we are from 0 to 3, pi y squared dx, and y is equal to, right here, 3x minus x squared. So there is our definite integral. Now again, because this is a squared, it's much easier to multiply that out. So it looks like this, from 0 to 3, pi 3x minus x squared times itself 3x minus x squared dx. And again, now I can multiply that out. So I am from 0 to 3. The pi comes along. When I multiply these out using area boxes or the FOIL method, I get 9x squared minus 6x cubed plus x to the 4th. All right, so there is your definite integral. Now we can solve this using the fundamental theorem of calculus. The first step is to take the antiderivative. So the pi comes along for the ride. This is going to be 3 power rules. So for the first term, the 9 comes along for the ride. We get 9x to the 3rd over 3. The second term, the 6 comes along for the ride. That becomes x to the 4th over 4. And finally, the third term becomes x to the 5th over 5. And it is from 0 to 3. Now let's simplify that antiderivative. So this right here becomes 3x cubed. This term right here, 6 over 4, I'm going to write that as 1.5. X to the 4th. Right here, if I pull out that 1/5, I can write that as 1/5, or I can write it as 0.2 x to the 5th from 0 to 3. So it helps to simplify your antiderivative. It's much easier to plug into your calculator. Now, the second step of the fundamental theorem of calculus is we take g of 3, we plug 3 into the antiderivative, minus g of 0. We plug 0 into the antiderivative. So when I plug 3 into this antiderivative, I get 25.45. And when we plug in 0, we get 0. So we have 25.45 units cubed. That is our volume. Now, a couple of things. Make sure that you put parentheses around that antiderivative because that pi has to be distributed. All right? To check your work, you can take the original definite integral and check with your calculator using Math 9. Okay, for number 3, we are going to rotate this parabola right here. We are going to rotate that across the y-axis. All right, so the first thing that you have to do when you're rotating it about the y-axis is you have to take your equation and you have to solve it for x. All right, so take my original equation, y is equal to x squared, and we must solve this for x. All equations, when you're rotating it about the y-axis, have to say x is equal to. So this is a pretty simple one. To solve this for x, we simply take the square root of both sides. So the square root of x squared is just x. So x is equal to the square root of y. So that's the first thing you want to do. Now, let's check out what our region is. We are rotating this from 1 to 4. So here is 1 right here. Here is 4 right here. So the region that I'm rotating looks like this. I'm highlighting it in yellow. It's that little piece right there. All right? It's nice to kind of reflect that graph across the axis of rotation. We're going to put in a horizontal rectangle because it has to be perpendicular to the y-axis. So there is what our rectangle is going to look like. And then our disk is going to kind of come up like this. All right, so the radius of our rectangle, of course, because it is a horizontal length, our radius is going to be in x. And the height, the thickness of our disk, because that is a vertical length, that is going to be a change in y. Okay, so our radius, x, and our height, dy. All right, so we set up our integral. It's going to look like this. We have from 1 to 4. Remember, the limits are along the axis of rotation, so the lowest part of our region, the y value there is 1. And the highest part of our region up here, the y value is 4. So from low to high, those are my limits. We have pi r squared, but my radius is x. So we have pi x squared, and my height is dy. All right, the next thing to do is, of course, to plug in what x is equal to. So pi x squared dy. My x, I plug in right here. X is equal to the square root of y. And then I would absolutely simplify that because the square root and the squared are going to cancel each other out. So it's going to look like this. We have from 1 to 4, pi y dy. And there is our definite integral. That should be a pretty easy one. Now we use the fundamental theorem of calculus to solve that. The first step is to take the antiderivative. Don't forget the pi comes along for the ride. The antiderivative of y using the power rule is simply 1/2 y squared. We use brackets to bring along the limits, and then we do our second step of the fundamental theorem of calculus. We plug in 4 and we plug in 1. So put the antiderivative into y equals and use your table. When I plug in 4, I get 25.13, and when I plug in 1, I get 1.57. All right, and my volume gives me 23.56 units cubed. So there is a rotation about the y-axis. Okay, and finally for number 4, we are going to rotate this parabola, x squared plus 2. We're going to rotate that about the y-axis. So here is our region from 2 up to 6 along the y-axis, and we're in quadrant 1. So the first thing we're going to do is we're going to put in a rectangle that is perpendicular to the axis of rotation. So that's going to be a horizontal rectangle right here. The radius, of course, is going to be x because it is a horizontal length, and the height, the thickness of that right here, because that's a vertical length, our thickness, our height is a dy. All right, I like to reflect and then show where that disk is going to go. There we go. All right, so let's set up our definite integral. We are from 2 to 6 along the y-axis. Your limits are along the axis of rotation. We need pi r squared, but again, our radius is x. Right here, horizontal, so it's pi x squared, and our height, the thickness, is dy. And then we can plug in what x is equal to, pi x squared dy. So remember, when you're rotating about the y-axis, you must solve your equation for x. So we're going to take our original equation right here, y is equal to x squared plus 2, and we're going to solve that for x. So the first thing I'm going to do is I'm going to subtract off 2. So I get y minus 2 is equal to x squared, and then I'm going to square root both sides. So x is equal to the square root of y minus 2. And this right here is what I'm going to plug in for x right up here. This x becomes the square root of y minus 2. Alrighty? Now let's simplify that, because that squared and that square root will cancel each other out. So our final best simplified definite integral is pi, and don't forget parentheses, we need y minus 2 dy. And there is our definite integral. Now we solve that using the fundamental theorem of calculus. The first step, we take the antiderivative. The pi comes along for the ride. This is going to be 2 power rules. Don't forget the parentheses. The antiderivative of y is 1/2 y squared. The antiderivative of 2 is 2y. And we use brackets to bring along our limits. That is the first step of the fundamental theorem of calculus. Find the antiderivative. The second step, now we plug in our limits. We plug in the top of the rectangle, the upper limit, we plug in 6, and we plug in 2. So we are plugging these values into the antiderivative. So put the antiderivative in y equals and go to your table and find these values. All right, when I plug in 6, I get 18.85. When I plug in 2, I'm getting negative 6.283. Remember, this minus and this negative are not the same, so that becomes a positive, and I add them together, and I get 25.13, and that is units cubed. All right, thanks, calculus.